Swayam Prabha. Digital India. Educated India.
Now it's time for us to look at some advanced concepts, namely functions and stacks. So what we have discussed up till now will take us till a certain point, but it will not allow us to write fairly difficult or complicated assembly programs. As a result, it is necessary to introduce a couple of slightly more advanced and complicated concepts, and the most important of that being functions. And to support functions, we need a software structure called a stack. So what is a function? So let's consider a C program. A function is essentially a block of code that achieves a certain specific task. So we give a function a set of arguments, and then for example, if there is a function to find if a number is a prime number or not, then the number is an argument to this function, and the result, a Boolean result of whether the number is prime or not, is what the function returns. So similarly, we should be able to write functions in assembly language as well, similar to a high-level programming language. So if you think about how functions will actually be represented in memory, it is something like this, as shown here, that it is we take a region of memory, put in all the instructions of the function here. So I'll just write ins to be short. So all the instructions, we put them in a continuous region of memory, and this region of memory, which starts at this point, the beginning, the first byte, so this is the beginning of the function. And so any function, so foo traditionally is the name of a function when we give an example. So in this case, this continuous region of memory stores all the instructions of the function. The data is stored somewhere else, we'll come to that. And any function will be identified by the address, the starting address of the first instruction. So to call a function, what do we need to do? So let's just go back to the previous slide. If the starting address is A, we set the program counter to A. So this is equivalent to jumping to the first address of the function. So once we do that, we can start executing the function, and after the function completes, we need to store the location of the program counter at which we need to return to. So if we consider a traditional execution of a program, we keep on executing, we go and execute some function, we execute the function and we come back. And then we start at exactly the same point. So we need to store the location of the point at which we return from the function. This is known as the return address. So this also needs to be stored. So essentially, what do we need to store? We need to store two things. We need to know what is the starting address of the function, which is A in this example, and then we need to jump back to a point which is the next instruction after the function call, and this is known as the return address. So let's take a look at the notion of the return address once more. So let's assume that we have a caller. So caller is the function that invokes another function. So the caller calls a function, and so we have a function called instruction, and let the address of this the call instruction be P. So then we call a function, which basically means that we jump to the beginning of the function. We execute all of its instructions. Then we have the ret instruction, which is the return instruction, where we again come back, and we come back to the instruction which is just after the function call. In simple RISC, since we assume that each instruction is 4 bytes, we start at address P and we return back to address P plus 4. This is the PC, the program counter of the return address. And So let me just maybe expand this example with some more details. So let's assume that the starting address of this instruction is A. So the call function is pretty much will change the value of the PC equal to A. We'll start executing this instruction. The return address is P plus 4 because that is the address of the next instruction. So when I do the ret instruction, when I invoke the ret instruction, it sets the program counter, the PC, equal to P plus 4. So now that we know how a basic function call works, let's look at a very simple example and see how exactly we pass arguments and return values to and from a function. So the example is like this, that we first, so what we want to do is we want to write a simple function that takes two arguments. So we can think of an add function. So I'm writing this example in C, where we have an add function and it takes two arguments. Let's say int x and int y, and it returns x plus y. So to implement this simple function in simple RISC, what we do is like this. So similar to C, we assume that we have a dot main label where the execution of the program starts. So it is customary to put a colon after the label. After this, let's set the value of registers. So we set R0 to 3 and R1 to 5. Then now we are introducing a new instruction called the call instruction. The call instruction jumps to a label. In assembly, what we do is that we designate every function with a label, which is nothing but the starting address of the first instruction. So we call .foo, so it jumps to this point. So the way that we write a function is actually very simple. We start with a label, just have all the instructions, and then a ret instruction at the end. So what we are doing here is we have set the values of registers R0 and R1. Then we call the function foo, which essentially means we jump to the label .foo, and at this label we add R0 and R1. We save the result in R2 and then we return back. So when we return back, what simple RISC is supposed to do is that it is supposed to take us to the instruction after the calling instruction, which is this instruction over here. So this is exactly what we do. We come back. At this point, the value inside foo is R0 plus R1, which is 8. Then what we do is we add 8 and 10, and finally we set R3 to 18. So the important takeaway points over here are that we are introducing two new instructions, a call instruction and a ret instruction. The call instruction is designed in such a way that we call, for semantics, the format of the call instruction is call and label. So in this case, we actually jump to the first address of the first instruction in the function. We execute the function and execute the ret instruction, which again brings us back to one instruction after the calling instruction. So how are we passing arguments? So in the previous example, we passed arguments via registers. We populated some registers, then the function read the registers. So here is, so this is one point where students typically confuse. So one thing that they need to know is that the set of registers is the same for the entire program. It's not that different functions have different sets of registers. So you can think of the registers as being shared. So if one function writes to a register, the other function can read from the register. So they see the same view of the set of registers, also known as the register file. So there is a space problem. The issue is like this, that we have a limited number of registers. So let's say in our case we have 16 registers. So we cannot pass more than 16 arguments. It's not possible for us to actually pass more than 16 arguments to the function. So this is called a space problem. So one way that we can actually solve this is if let's say the caller function puts in its arguments into a region of memory, and then the callee function reads the arguments from there. Also, there is an override problem, which is what if a function calls itself, like a recursive call. In this case, the callee will overwrite the registers that the caller may need, and this is a problem. So we'll propose another solution. It's called register spilling. So we'll discuss both of these solutions in detail over the next few slides. So when I look at register spilling, the idea is like this, that let's say I have one function foo, which is calling another function. Let's call it foo bar. Foo bar does something and comes back. So it is possible that foo bar overwrote some of the registers that foo may require, right? So maybe foo requires register R1, and then you go to foo bar, then it sets R1 equal to something, which is fine, but the thing is maybe we are not interested in that value, and again when we use R1 we might get the overwritten value and not this value. So for that, what we can do is we can use a technique called register spilling. The notion of spilling is like this, that the caller can save the set of registers that it needs to use. Then it can call the function, and then it can call the function and subsequently restore the set of registers after the function returns. So this is known as the caller saved scheme. So here essentially what you do is that you save a set of registers that you plan to use in the future using store instructions. Then you call a function, the function does something, and again the function returns to the next instruction. Subsequently we have a set of load instructions that load the values of these registers that were stored to memory back again. So let's say in the store we save the value of registers to memory, and in the load we read the values of what we had stored back into our registers. So this particular thing is called a caller saved scheme. In a callee saved scheme, what happens is that the function that is called, which is called the callee, that saves the registers that it might potentially overwrite, and later on it restores their value when it is about to return. So if I want to think about this, so conceptually in a caller saved scheme, the way it works is something like this, that we first save our registers, we store them to memory, as you can see over here. Then we call the callee function, and then we restore the registers, we restore the values of the registers. In a callee saved scheme, the idea is that the caller does not do anything. So it's absolutely, so it assumes that all of its registers, unless of course you mutually decide that a certain register is going to contain a return value, all of its registers will maintain their value. The callee will first save the registers, subsequently do its work, and just before returning restore the value of the register. So there are two schemes. They have their pluses and minuses. So we will discuss a little bit of that, and most of this is actually there in the exercises at the back of the chapter. But students should think when the caller saved scheme makes sense and when the callee saved scheme makes sense. So what are we doing? Our solutions are like this, that we are essentially using memory and spilling, which also uses memory, to solve both the space problem as well as the overwrite problem. However, using this memory-based approach for both solving the space problem and the override problem has issues. So let me just at this point slightly recapitulate what these problems are. The space problem basically says that we run out of registers while passing arguments. So for example, let's say a function takes 100 arguments. We don't typically write such functions, but we can, theoretically we can, but it's very common to write functions with maybe 8, 9 or 10 arguments. So if each of them is in a register, we will run out of registers to do other work. That's the reason we will have a serious space problem while especially passing arguments around, and also managing them inside a function. The main reason being that we need registers for other work also, like saving temporary variables and so on, temporary values and temporary variables and so on. So that's why the space problem is important, and the override problem is definitely very important. The main reason being that we only have 16 registers. Out of that, we will see that we are typically not allowed to use more than 14 for general purpose work. So it is now, let's say one function calls another copy of itself or other functions, then they will overwrite the registers that they require, because all of them see the same view of the register space. That's the reason it is necessary to save or store registers in memory and read them back again. This is known as the overwrite problem, and we saw two methods of fixing it. It's called spilling. So the two approaches for spilling were, so they were caller saved and callee saved. So however, there needs to be a very, to have both of these schemes running, there has to be a strict agreement between the caller and the callee regarding the set of memory locations that are being used. So the reason for this is that let's assume the caller saves its registers in a certain region in memory, right? So let's say it is this region. Then the caller calls the callee, and the callee also starts saving its registers in this region. Then clearly they will start interfering in memory, and this will not work out. So the regions of memory that are to be used by different functions has to be known a priori, and this is a problem. And then once a function has finished its execution, it will not need the space that it had used to store registers for spilling. This space has to be reclaimed, right? So we have to sort of somehow mark this space to be empty such that it can be used by other parts of the program. So there's a need to reclaim this space. So this makes things pretty complicated, and the root of all the problems is the space problem and the overwrite problem. So to make our life simple, let's define an activation block. An activation block is a region of memory that stores certain information about an executing function. So let's assume a function foo that takes a single argument arg1. It has three internal variables a, b and c. A is set to 3, b to 4. C is a plus b plus arg1, and then we return c. So in the activation block, there are a couple of things that we need to save. The first is the argument. The argument will get saved in the argument section inside the activation block, which is essentially a region of memory, and we are sort of dividing the region into multiple sub-regions. So in one region we save the arguments if required. In other case we save the local variables, which in this case are a, b and c. The local variables are saved in this region, and then we save the return address again if required, and we have a register spill area where we spill registers if required. So the activation block is essentially the region in memory that is task to keep all the values that are required for a function to execute. And as you see, after a function executes and after we return C, the activation block is not required. So how do we use the activation blocks? So let's say that we have caller saved spilling. So before calling a function, we spill the registers. Then we allocate the activation block of the callee. We write the arguments to the activation block of the callee. If they don't fit in registers, if there are one or two arguments, they can always be passed via registers. But if there are more than one or two arguments, then these arguments need to be passed via memory. And the way we do that is we write the arguments inside the activation block of the callee, and then we call the function. So just to illustrate how this works, let me draw a small diagram. So let's assume that we have the caller function executing. So we execute one instruction, another, and then we decide that we need to call a function. So the first thing, since we assume caller saved spilling, the first thing that we do is that we spill the registers. Spill the registers basically means write the values of the registers that we are interested in into the activation block of the caller. Subsequently, we call the call instruction. The call instruction transfers control to the callee function. We start executing all the instructions. And before we before the caller calls the callee, one more thing that it can additionally, so this is one example where the arguments are being passed via registers, but we can alternatively also pass them via the activation block. So in this case, what will happen is that we spill the registers, then we allocate, then what the caller does is it allocates an activation block for the callee. So I'm writing alloc. Then it writes the arguments, function arguments, to the activation block of the callee function. And then we have the call function. We have the call instruction where we call the callee. So inside the called function, which is the callee, what we do is like this, that we first read the arguments and transfer them to registers if required. We save the return address if the called function can call other functions. We allocate space for local variables, and then we execute the function. Once the function ends, we restore the value of the return address register if required. We write the return values to registers, if required, but if there are a lot of values, or if it's one large value, we can write it to memory also, which is the activation block of the caller, and then we destroy the activation block of the callee. So this is the broad sequence of actions that we do. So I've deliberately been vague at certain points. The reason being that there are many more details that will sort of come in the next few slides. But the main idea is, the main take-home point here is that memory is divided into many regions. So one of these regions stores the activation blocks. What is an activation block? It's a continuous region of memory that stores the execution context of a function, and the execution context contains the arguments of a function, space for saving its internal variables, space for saving the registers that it spills, and also the return address if the function is calling other functions. And so pretty much that's it. And once the function finishes execution, the activation block of the function is destroyed. So we have introduced two functions, call and ret. So we'll discuss them in slightly more detail. So the main idea of the ret instruction or the return instruction is that once the function ends, we call the ret instruction and return back to the caller. What does the caller do? It retrieves the return values from the registers or from its activation block, or sometimes, so it depends upon the convention that if, let's say, there is one large return value and many return values, where are they written? So they might be written, so they are typically written into registers or in the activation block of the caller function. Then in this case, since we assume caller saved registers, we restore the spilled registers and we continue. So up till now we have discussed the main idea of an activation block. We have not really discussed more about the exact ways in which we want to implement them. But the basic idea is clear that we have two instructions, call and ret. The call instruction, what it does are a couple of things. Let me quickly write down. So the call instruction, what it does is like this, that it transfers the control to the beginning of the callee function. That's one thing that the call instruction does. And additionally, what it does is that it saves the address of the next instruction as a return address. So this can be saved in many places. So let's not talk about where exactly it is saved, but let's just refer to this piece of information as a return address. And this can optionally be saved in the activation block of the callee. Subsequently, the callee does its job. It computes its result. The return value, which is what is the result of the function, can come back either via registers, that is the first option. The second option is that it can come back also via memory. In this case, what the callee does is it writes back the result into the activation block of the caller. So this is also possible. Now, the idea is somewhat like this, that so after the callee function finishes, we invoke the ret instruction, the return instruction. The return instruction comes back to the return address, which is just one instruction after the call instruction. And prior to executing the return instruction, we have to destroy the activation block of the callee. So the question now is that all the information of an executing function that is stored in the activation block has to be created millions and millions of times during the execution of a program. The reason being that a program typically, function calls are very common instructions, and even in 1 second, millions of times functions are called. So we need a way of managing activation blocks, ensuring their very fast creation and deletion. And we need to look at a certain pattern to make this a very quick operation for all of us. Let us now try to look for a pattern of executing function calls and see if there is something that can be done to actually represent this information better and also create activation blocks very, very easily. So let's consider a main function which calls two other functions, test and foo. So let main call test, so the activation block of test will be created. And let test call test2, so the activation block of test2 will be created. Once test2 is done, it will return. So the activation block of test2 is not required anymore, so it can be destroyed. And once test is done, test will return, so the activation block of test is not required anymore, so it will be destroyed. Subsequently, main will call function foo, so the activation block of foo will be created. So let foo call foo bar, so the activation block of foo bar will be created. And let foo bar call foo bar bar, so the activation block of foo bar bar will be created. Similarly, when we come back, these activation blocks will be destroyed in this sequence. So this is shown in the next slide. So if we consider the activation block of foo, then foo bar will be created. The activation block of foo bar will be created. Then the activation block of foo bar bar will be created, and then it'll be also be the first to be destroyed. Then the activation block of foo bar will be destroyed, and then lastly the activation block of foo. So what do we see? The behavior here is last in, first out. So foo bar bar was the last, was the latest function to be executed, and it is also the latest function whose activation block will be destroyed. So whenever we hear the term last in, first out in computer science, it reminds us of a data structure called a stack, where a stack is something as simple as a stack of books, right? So we just stack one over the other. So the book that we added, the last is also the first that comes out. So similarly, we can store activation blocks as a stack, where essentially we store foo, then we store foo bar below it, we store foo bar bar below it. And so these can be treated as memory regions. So traditionally stacks are downward growing. What this means is that if we want to create a new activation block, we create it in a lower memory address as compared to the previous activation blocks. For example, let's consider an example, make things easier. Let's say that the stack begins at location 1000. Let's assume that the size of the activation block of foo is 100, foo bar is 100, and foo bar bar is 100. So the first 100 bytes can be consumed by the activation block of foo, the next 100 by foo bar bar, and the next 100 by foo bar bar. Subsequently, we delete this, so we store only 200 bytes. Subsequently, we again delete this when foo bar is over, and we store only bytes from the region 1000 to 900. So this is where the notion of a stack comes from, that a stack is actually a programming language concept where it denotes how data is stored, and the last in, first out abstraction holds that a piece of information that is inserted into a stack at the end is also the first to come out. So this is actually very similar. If you see the pattern in which functions execute, they exactly execute like a stack. So that's the reason we can store their activation blocks also as a stack. So traditionally what you do is that stacks are a region of memory, and they typically start at the highest region, which in this case is, let's assume the largest address we have is 1000, and subsequently we start storing their activation blocks in the manner that I've shown. So maybe the first one can be stored from 901 to 1000, and the second from 801 to 900, and the third from the addresses 701 to 800. So now working with the stack, so we allocate a part of the memory to save the stack. As I had mentioned, stacks are downward growing. So we dedicate one register in our set of 16 registers, particularly register 14, R14. We call it the stack pointer register. It is also called as SP. It's also referred to as SP. So it's either SP or as R14. So this points to the beginning of an activation block, and so basically it also sort of points to the top of the stack, right? So for example, if the stack begins at this point and then we have activation blocks, this is where it ends. So this is where exactly the stack pointer should point. So it's basically the beginning of the next activation block, or where the stack is ending. So allocating an activation block is very simple. All that we do is we subtract the stack pointer by the size of the activation block. If it's 100, the new stack pointer will point to this location, and this region in memory becomes its activation block. So essentially we have booked it. We later on need to fill it with information. Deallocating also requires a single instruction where we essentially do SP is equal to SP plus the size of the activation block. In this case, if it's 100, then we sort of fold it back up again So essentially allocating and deallocating an activation block is very simple. To allocate an activation block, we subtract the stack pointer by the size of the block, which is a constant and should be known beforehand. Similarly, to deallocate the block, what we do is that we add the size of the block, which is a constant and is known beforehand, to the stack pointer. So it's very simple. Allocating and deallocating is only a single instruction, which is also what we wanted. So we are using the property, the last in first out property, which has made our life very simple. So what has the stack solved for us? It has definitely solved the space problem. So we can pass as many parameters as required via this activation block mechanism. So, if the number of parameters are few, the number of arguments to a function are few, they can be passed via registers. Otherwise, they can be stored in regions within an activation block and they can be passed. The stack has also solved the override problem. So now functions don't overwrite each other's data. They have their own regions in memory where they write their own temporary variables. Managing the activation blocks is much easier because they're saved in a stack. So creating new ones or getting rid of old ones is very easy. We just need to manipulate the stack pointer, that's all, using regular add and subtract instructions. So the stack in most instruction sets is actually a software construct. So there is a broad agreement that a certain register needs to be treated as the stack pointer. But other than that, it is mostly managed in software, which basically means that when you're writing assembly code, you have to explicitly manage the stack. So we'll see an example of that. But essentially, the programmer or the compiler have to add instructions to explicitly manage the stack and sort of increment and decrement the stack pointers and create the activation blocks as and when required. Let's now discuss the call and ret instructions. So we have introduced the notion of calling a function and returning from a function, but that was more from a high level conceptual theoretical angle. It was not from a practical point of view of how it's implemented. So before actually I describe these instructions, it would be noteworthy to first introduce the return address register, which is actually a register in our simple RISC instruction set, but there are similar concepts in ARM and x86, as we shall see in the next two chapters. So what we shall do is that let us designate the 15th register R15 as a return address register. So we'll also refer to this register as RA or R15 interchangeably. So what the call instruction does is that the call instruction computes the address of the next instruction, which is the current PC plus 4, and saves it in RA, the return address register, and then subsequently it sets the program counter to the address of the function that we want to go to. So the assembly language semantics is call label, where label is essentially pointing to the first instruction in the function, and the way that this gets translated in hardware is that we set the return address and we set the PC, the program counter, to the address of that corresponds to the .foo label. Note that we'll have these dot marks before labels. It's more of a convention, but the simple RISC interpreter does not require dots in front of labels. The return instruction is very simple. We read in the contents of the return address register to the program counter. So this is essentially like a jump. So in our register file that contains 16 registers, the last two registers, namely R14 and R15, are reserved for special purposes. R14 will be the stack pointer and R15 is the return address register. So all the other registers can be used by the program. So here again there is some amount of semantics that different instruction sets typically define. So it's not specific to simple RISC, but typically R0 and R1 would be used to pass parameters, and the rest of the registers will be used to process temporary values. So here again, as it's written, for a call instruction, you put PC plus 4 in RA and jump to the function, and in the return, in the ret instruction, you put the value of RA in the PC. So it's time that we write our first program in simple RISC assembly that uses the stack as well as the call and ret instructions. So let us write a recursive variant of the factorial function. So in this case, this is a C program. We'll start from this line. Let's compute the factorial of 10. So inside the factorial function, we'll first have the base case. So the base case says if num is less than equal to 1, return 1. So this is where the recursion will terminate. Otherwise, we return num times factorial num minus 1. So here we compute 10 times 9 times 8 times 7 and so on. So to convert this into simple RISC is actually easy. So let us start with the dot main label where the main function will start. We move 10 into R0 because we'll be computing the factorial of 10, and then we call the factorial function. So this takes us way to the top over here. So let's first test for the base case that whether we should continue the recursion or not. So as we shall see here, we compare the number that's coming in, the argument R0, with 1. So if there is equality, it basically means that R0 is equal to 1. So we can just return. And so we jump to the return point, which is over here. If R0 is greater than 1, then we need to do the recursion. So we jump to dot continue. Otherwise, the only case that is remaining is R0 is less than 1. Then also we jump to the return label here. In the return label, we set the result, which is the result of the factorial function, to 1. Because factorial of 1 is 1 and factorial of 0 is 1. So we set the final result R1 to be equal to 1, and we return from the function. So when we return, we come to the next instruction after call factorial, and this will find the result in R1. So you can think of the factorial function as taking its argument in R0 and then returning its result in R1. So the main fun is in this part, in the continue part, which is actually the recursive part. So the first thing is that we create the activation block over here. So we create space on the stack. So we create the activation block. All right. If we want space to save two variables, so two variables means two integers. If one integer is 4 bytes, so for two integers it would be 8 bytes. So what we do is that we create an activation block here. We subtract 8 from the stack pointer. So essentially this instruction has sp equals sp minus 8. So we create some space. So if the original stack pointer was over here, the new stack pointer will be, so 4 bytes, another 4 bytes, the new stack pointer will point here. Now what we do is that, since we are calling another version of the factorial function itself, it is necessary to save some information on the stack. Otherwise the called function, the callee, will overwrite those values. So what we do is that at the stack pointer, which is essentially if this is a new location of the stack pointer, the top 4 bytes, this location, we save R0, which is the argument, which is essentially what came from the function that called this function. So we save it over here. And in 4SP, which is the next location, we save RA, this instruction over here. We save the return address because this also might get overwritten. Subsequently, we subtract 1 from R0, which is essentially num minus 1, and we call factorial once again. So essentially, we call one more copy of the factorial function. So that will again call one more copy of the factorial function and so on. So the same way that recursive functions execute. So at this point, the assumption is that the factorial of num minus 1 is stored in R1. So that is the assumption. Because all factorial functions, including the base case, are supposed to keep the result in R1, and that's the way that we have coded it. So that's okay. We will use the value of R1 later. Let us just restore our values because we had spilled some registers. Let us restore them. So recall that our stack pointer, which is supposed to have remained untouched. So we'll see how. Let us load back the value of R0, which is something that we had stored over here. Let us load back the value of RA, which we had stored over here. So basically the values of RA and R0 are restored, and this particular scheme that we have followed here is a caller saved scheme because the caller is saving the registers that it needs and later on restoring them. Subsequently, we multiply R0 times R1. So R0 is basically num and R1 is factorial of num minus 1. So essentially we are computing factorial n is equal to n times factorial n minus 1, and the results are being saved in R1, which we have always wanted to do. Now since the result is in R1, let us get rid of our current activation block. So recall that we started the activation block by subtracting the stack pointer 8 from the stack pointer. Let us now delete the activation block by folding the stack pointer back. So what we do is we set the stack pointer's value back to its old value. So this is done by adding 8 to the stack pointer. So think about this. At the beginning of the function, the stack pointer was here. We needed to save 2 local variables. We need to spill 2 registers actually. So the new stack pointer pointed here. Once the function was over, we restored the value of the stack pointer to again point to where it was originally pointing. After this, since the value is in R1, we return back. So it is easy to prove by any technique that uses mathematical induction that this program will always work. In the sense, every copy of the factorial function saves the result in R1. So the base case at the dot return label saves the result in R1, and even the recursive case saves the result in R1. The reason being that it calls many copies of itself. Each of them save the result in R1. Finally, in this line over here, we multiply n times factorial n minus 1 and save it in R1. Lastly, it is very important to delete the activation block, which is being done in this line. Alright, so here is a chance that we get to introduce one instruction that does nothing at all. So it is a no-op instruction that does nothing at all. Why on earth would we require it? This will be common. This will be explained to you in chapter 9 when we discuss pipelined processors. That is when I'll explain why we need this particular instruction, not now. Alright, so we have seen up till now a basic overview of assembly language, the syntax of assembly language, a simple instruction set. Then we have looked at functions and stacks, which is an advanced feature in programming languages. So it is also possible to implement other kinds of features such as object-oriented programming and so on. But these are all variants of this, and I didn't want to heavily complicate it. But users would realize that using the basic instruction set provided, a lot of these high-level features can be implemented. Typically, in most instruction sets, we only designate two kinds of registers as special. One is the stack pointer, as we have done, and the other is the return address, RA. ARM and x86 have some other special registers. We'll talk about it when we discuss those instruction sets. Now let's look at an encoding of the instruction set in binary bits. So basically, if you have 32 bits, we need to be able to encode all the instructions, because after all, the computer does not understand assembly, it only understands zeros and ones. So every assembly instruction needs to be encoded in simple zeros and ones. So we have 32 bits to encode the instructions, because it's a 32-bit instruction set. And we up till now have introduced 21 instructions. So let's start out by assigning an opcode, an operation code or an instruction code to every single instruction, and the instruction code has to be unique. For example, so there are 21 instructions, so we will need 5 bits. Right? Why 5 bits? Because 4 bits will not do. We can only encode 16 instructions, so we need 5 bits. So the add instruction gets a code of 0. Then we first have all the arithmetic instructions. Then we have the load and store instructions. And lastly, we have the branch instructions. So why instructions have been assigned, this kind of codes will actually be clear to you in chapter 8 when we discuss decoding. So all that I can tell you right now is that it should be easy to find out, what is the type of an instruction. So for example, the branch instructions, I can easily find that an instruction is a branch by actually taking a look at the most significant bit, which is 1. Similarly, other kinds of tricks have been put for other kinds of instructions. So we'll get a chance to discuss all of this in the chapter on decoding. Alright, so up till now, we have our basic instruction format. We have a 5-bit opcode, and the rest of the 27 bits is there to encode the rest of the instruction. And here is a quick summary of the instruction set that you can actually, mark down for your own use, because this would be very helpful in the chapters on processor design. So every instruction first has the instruction name. Then RD is the destination register. So let's say RD is the destination register. RS1 is the first source operand, right? RS2 is the second registered source operand, and IM is an immediate. So as we can see, all arithmetic instructions are of the same type. You first specify the destination, then the first source register. The second operand can either be a register or an immediate. Then we have the compare instruction, which does not have a register destination. Subsequently, we have the logical instructions, which also have the same format. And also the shift instructions having the same format. The no-op instruction is essentially a zero address instruction. It does not take any operands at all. The load instruction, this should actually be a comma. So the load instruction essentially takes the first source register and an immediate and saves it in the destination. The store instruction is somewhat special in the sense that it does not actually have a register destination, but we shall see later that a compromise needs to be made, and this is what the format of the store instruction should be. mainly because we'll not have enough space, but this is best described later. We have a slide for it. Subsequently, you have the branch instructions. So in assembly language, all of the 5 branch instructions branch to a label, but actually when we shall encode it in hardware, all of these 4 branch instructions, I'm sorry, not ret, but these 4 branch instructions will actually jump to an offset. So essentially it will be PC plus the offset is what the branch instructions will be jumping to. Right, an offset relative to the current PC. There are some more tricks, we'll discuss that, but essentially it is an integer offset that needs to be added to the current program counter, which will become the new program counter. So we'll essentially come back to both of these issues. One of them is the format of the store instruction, and the other is the offset in the branch instruction that we shall use. And the ret instruction is simple. It's a simple zero address instruction, so it doesn't take any arguments. So let's first look at the low-hanging fruits, which are the NOP and ret instructions. So since they don't take any arguments, their encoding is very simple. They will only have the 5-bit opcode, and the remaining 27 bits are useless, so they need not be used. And all that we require is the 5-bit opcode, which is in the most significant position. These are our zero address instructions. Now let's look at our one address instructions. So we have 4 such instructions. They are call, unconditional branch B, branch if equal BEQ, branch if greater than BGT. So they use what is called the branch format, which we'll define right now. The top 5 bits remain the same, the 5-bit opcode. The remaining 27 bits specify an offset. So it's PC relative addressing. So this is a number, it's a signed number which is added to the PC. So it essentially we can add something or subtract something. So as I said, it's a 27-bit signed number which is added to the PC. Now here is a trick that should be mentioned. So the trick is something like this, that let's assume that the offset points to a byte. So all our instructions are 4 bytes each, right? So if all our instructions are 4 bytes each, and we assume that all instructions start at an address that is a multiple of 4, so then we will have addresses of this type: 1000, 1004, 1008, and so on, right? So all of these numbers are multiples of 4. Say any number that is a multiple of 4, when it is written in binary, which is a language that the computer understands, its last 2 bits will be 00. Subsequently, we'll have some bits. So then the obvious response would be that let us not waste space in specifying 2 bits whose value we already know, which are 0 and 0. So it's a much better idea to instead work with a simple assumption. The assumption is that all instruction addresses, so let me just write it down for added emphasis. Are a multiple of 4. If we make this assumption, then any offset, if it points to a byte, the offset will also be a multiple of 4 and its last 2 bits will be 0 and 0, which is not something that we want. So instead of making it a byte offset, we make it a word offset. So what is a word? A memory word we have defined before, but let me just define once again. A word is basically 4 bytes. So a word offset is basically the number of additional memory words. So let's say if the word offset is 1, this means that the byte offset will actually be 1 times 4, which is 4. So the byte offset is equal to the word offset times 4. So the actual address that we will compute in this case will actually be PC plus offset times 4. And the reason that we are doing this is because the actual address is a byte address, right? So this precisely points to a byte. But since we are assuming that all the addresses are a multiple of 4, we need not waste 2 bits for storing the offset because bits are very valuable. So we actually save the word offset, which is the number of memory words that a certain instruction, number of memory words between the current PC and the branch target, right? The target of the branch. So this offset can either be positive or negative, but in any case, it's a word offset. So to get the byte offset, we multiply it by 4 and we add it to the PC. Let's now look at the 3 address instructions that we have. So all our arithmetic instructions are 3 address instructions. All our logical instructions are 3 address instructions. And also all our shift instructions are also 3 address instructions. The standard format of the 3 address instruction is the opcode, the destination register, the first source register, then either a second source register or an immediate. So the first fork point, the decision point that we have, is to resolve whether we'll use the second source register or an immediate. So let us use the I bit to specify if the second operand is a register or an immediate. So if I is equal to 0, let's say that the second operand is a register, and if I is equal to 1, let's say that the second operand is an immediate. So basically, this is one extra bit that we need to accommodate in our instruction format, and its only role is to say whether the second operand is a register or an immediate. After that, we need to encode the value of the registers. Since you have 16 registers, we would need 4 bits to specify a register. So we'll see what the format looks like in the next slide. So what we have done here is that we have reserved space for our 5-bit opcode, which is the first thing that we need to do. After that, we have the I bit. So we are discussing the register format here, where the second operand is a source register. It's not an immediate value. So basically, in this format, the first 5 bits will be the opcode, and the I bit will be 0 because the second operand is a register. But this will nevertheless require 1 bit in our format. Then we need to specify RD, which is the destination register, the first source register, and the second source register. So each of these is 4 bits because we have 16 registers. So it will take 4 bits to encode them. We'll have 4 bits each. So the total number of bits is 5 plus 1, 6, plus 4, 10, 14, and 18, which is fine. So we were able to encode such kind of instructions in 18 bits, which is less than 32. So we will refer to this particular encoding format as the register format. Now let's consider the case where we have a 3 address instruction and the second operand is an immediate. So we'll start the same way. We'll have a 5-bit opcode. We'll have 1 bit for the immediate. So a 1 bit over here, and its value needs to be 1 because the second operand is an immediate. Then we'll have a register destination, 4 bits for that. The first source register, 4 bits for that. So total number of bits we have consumed up till now is 5 plus 1, 6, plus 4, 10, plus 4, 14. We have 18 bits left, which is exactly what we need. So we'll have a 16-bit immediate, and we can put in our 2 modifier bits over here. Recall that the modifier bits have, we defined 3 kinds of modifiers. 0, 0 is a default modifier. 0, 1 is a U modifier where we place the 2 bytes at the MSB positions. no, I'm sorry, 0, 1 is the unsigned modifier where we place the 2 bytes at the LSB positions, right? So basically these are the 4 bytes. Then with the unsigned, the 2 bytes were placed over here. And 1, 0 is the H modifier where they were actually placed in the MSB positions. So we will, since we have 3 modifiers, we'll require 2 bits to encode them. So these 2 bits can be stored over here just after the first source register. The 2 bits can be saved over here. Subsequently, we can store a 16-bit immediate, which is a signed 2's complement number. So as we can see, this format is very tight in the sense all the bits are being used. The total, all the 32 bits, every single bit is being used, and every bit is associated with storing some or other information associated with the instruction. Now let's take a look at 2 address format instructions like compare, not, and move. So we'll use a simple solution which is used in many other areas of computer architecture as well. We'll use the 3 address format. We can use either the immediate or register formats, but we'll not use every single field. So we'll keep some fields unoccupied. For example, the compare instruction, it does not have a destination. So we'll do nothing with the destination field, but we can keep the first source operand, the first source register, and the second operand, which can either be a register or an immediate. The move instruction will not have the first source operand, but will have a destination register, and the second source operand can either be a register or an immediate. Similarly, the not instruction will be similar to the move instruction. It will not have a source register, it will not have its first source register. It will have a destination register, and we'll have the rs2/im where we will have either a register, it will have a single operand which can either be a register or an immediate. So we'll use the rs2 field. So in this way, we have essentially, we are ensuring that our decoding hardware, which is the hardware needed to understand an instruction, we are ensuring that that hardware is simple, because we will have only a very few number of predefined formats. So up till now, we have only defined the branch format, the immediate format, and the register format. All the instructions we are trying to fit in those particular formats. Let's now discuss the load and store instructions. The load instruction has a register destination. So we are using the first 5 bits for the opcode. The immediate is 1. There is a register destination. The base register will save in the rs1 field. It has an immediate, which is the offset. So the immediate can be stored in the immediate field. So this is exactly the immediate format that we are using for the load instruction as well. So just to repeat, the load instruction has a register destination RD, which is saved over here. It has a base register, which we are using as the first source register rs1. It has an immediate, which we are considering to be the second operand. Let us now discuss the slightly strange case of the store instruction. And so hopefully after the end of this slide, readers will appreciate some of the trade-offs that need to be done by computer architects to ensure that their hardware is simple and everything remains elegant. So the case of the store instruction is somewhat like this, that in the store instruction, we have actually 2 sources. One of them is a register source, which is which provides the data that needs to be stored in a memory address. In the memory address, reg2 is the base address and im is the offset. So essentially it has 2 register sources, reg1 and reg2, from which we get data. The destination is memory, so there is no register destination, and there is one immediate. So we cannot fit this in the immediate format because the second operand can either be a register or an immediate. not both, and we have two sources. So what do we do? Should we define a new format for store instructions? Answer is maybe not. Let's try to reuse some existing format. So let us make an exception and use the immediate format. So let us use the RD field to save one of the source registers. So let's say we store RD. RD means it contains the register whose value is being stored in memory. We store this in memory. The base address is in RS1 and the offset is in IM. So if we do this trick, readers will appreciate that we are not defining a new format. What we are doing is that we are first using the first 5 bits to store the opcode. The immediate bit over here, which is one more bit, is 1, which means an immediate exists. The register whose value needs to be stored is actually being stored in the RD field, which is fine. It will introduce some complexities in the processor. We'll take care of it. The first source register RS1, which is also the base register of memory, is being stored over here. And finally the immediate, which is the offset, because we are using register indirect addressing mode that has a base and an index. So in this case the immediate is being stored in the remaining 18 bits. So this is a tight format. All 32 bits are being used. So in that sense we are not wasting any bits. But the question is that if you think about it, still an exception is being made. The reason being that the store instruction has a memory destination, it does not have a register destination. So we don't have any other instruction in our instruction set which has a memory destination. So the store instruction in that sense is special, but we don't want to define a new format because that will make the hardware, the decoding hardware, pretty complex. So we would rather use the same format and use the fields in the format slightly differently. So that's the reason the register whose value needs to be stored is being saved in the destination register field. This is the exception that is being made. And then the base register and the immediate are being stored at the respective places for the first source register and the offset. So what is the summary of instruction formats right now? The summary is something like this, that the opcode is saved in the MSB bits of 28 to 32. So in the branch format, the summary is in bits 28 to 32. The opcode is saved. The offset is saved in the remaining 27 bits. In the register format, same thing. The top 5 bits always contain the opcode. Then we have one bit to encode the fact that we have a register immediate or either a register operand or an immediate. So in this case, we first save the register destination, the first source operand and the second source operand, which in this case are all registers. In the immediate format, we also have an immediate bit which is set to 1, which means that the second operand is an immediate. We save the register destination, the first source register, and the second operand is an immediate. It's an 18-bit immediate. So the 18-bit immediate is divided into 2 parts. One part is a 16-bit number, which can be interpreted as signed 2's complement number if required, and the top 2 bits are the modifiers. So we support 3 kinds of modifiers. One is the default, where the 16 bits are interpreted as a 2's complement signed number. Then we have 2 modifiers, U and H. U is unsigned, where the top 2, where the immediate is interpreted as an unsigned number, and H is H basically says that the immediate will be left shifted by 16 positions. So this is where our description of the simple RISC instruction set ends. So mind you, this was a very simple instruction set. This is where the simple in simple RISC comes from. Real world instruction sets are much more complicated. They have far more instruction modes and kinds of instructions, types of instructions, and they also take many different kinds of operands. There are many special conditions and flags and so on. But it is important for a reader to understand at least the nuances of designing an assembly language from scratch. What are the problems that can come? For example, in our case, we had a problem with the store instruction, so we made an exception for the store instruction. So this is a typical, engineering trade-off that needs to be done. Sometimes for the sake of simplicity and elegance, it is important to make some trade-offs such that the hardware remains simple. Then we designed a full encoding format for our simple RISC instruction set, where we showed how using 32 bits all the instructions can be encoded into zeros and ones. So now we will look at chapters 4 and 5, where we will discuss two real world instruction sets, ARM and x86, and readers can use them to actually write actual assembly code in big software. But it is important to understand the concepts presented in this chapter before going to those two chapters. So let us end at this point and see you in the next lecture, where we will be discussing the ARM instruction set.